Hi, welcome back. We're in Lecture 20, Segment 2, and the topic is binary logistic regression. In the first segment, I gave you an overview, and we talked about the components of binary logistic regression. Now, in this segment, let's do an actual example. So the example I want to use in this segment and to demonstrate binary logistic regression is based on what's called mock jury research. In particular, a study by Diamond and Casper in 1992. The way mock jury studies work is researchers who are interested in psychology and law, they have people watch a video of certain phases of a trial. In this example, let's assume that the people watch a video of the sentencing phase of a murder trial in which the defendant had already been found guilty. So they're watching the sentencing phase now, where they have to make a decision about how this person who's been found guilty, how they'll be treated. The issue for the jurors to decide is a very serious one. It's whether they should vote for the death penalty or not, a life term in prison. So we're going to assume that the data were collected in this example, because this is the way it worked in the Diamond and Casper study. Let's assume that the data were collected pre-deliberation. So what I mean by that is before the jurors got together to deliberate and discuss the situation, each juror was just asked, well, what do you think? How do you think you'll vote on this decision about the death penalty or a life sentence? So what that means is we have an outcome variable that's 0 or 1. Right? It's categorical, it's binary, so we'll give it a 1 if they vote for the death penalty, we'll give it a 0 if they vote against the death penalty. And what Diamond and Casper did is they looked at a bunch of predictors, and what these predictors are is they're attitudes that the jurors themselves feel about the defendant, about the role of the death penalty, and about just sentencing in general, and how the criminal justice system should work. So we'll look at a bunch of these predictors. I've used just sort of the shorthand for them here, but let's look through each one of them. So by danger, I'm referring to the dangerousness. So the individual's belief as to the future dangerousness of the defendant. So how dangerous do you think this person is or will be in the future? On a scale of 0 to 10, just rate that. Rehabilitation. So the individual's belief as to the importance of rehabilitation as a goal of criminal sentencing. Punishment. Individual's belief as to the importance of punishment as a goal of criminal sentencing. Gen det is my shorthand for general deterrence. So this is asking the individual jurors, just what are your beliefs about the importance of general deterrence as a goal of criminal sentencing? That is, should sentencing deter the general public? That's general deterrence. Versus specific deterrence. So what's the importance of deterrence as a goal of criminal sentencing to defer this specific defendant? So general deterrence, specific deterrence, and then finally incapacitation. An individual's beliefs as to the importance of punishment as a goal of criminal sentencing. So we're doing a multiple regression here, but the general linear model, remember that mathematical framework we talked about in the context of multiple regression, the general linear model is not going to work here because, remember, it assumes a linear relationship between x and y and assumes a normal distribution in the outcome variable. Well, we don't have that. We have a binary outcome variable that can only take on 0 or 1. So we need to do that logit transformation on the left-hand side of the regression equation. If we do that, then we can get a predicted score that will fall between 0 and 1, and we can make a guess as to whether this person's going to vote for the death penalty or not, based on their predicted score on this transformed y variable. This logit transformation is a feature of an even more general mathematical framework than the original GLM we talked about in the context of multiple regression. And the name of that is the generalized linear model. I know it sounds almost exactly the same as the general linear model, but it's very different. It's called the generalized linear model, which allows for lots of different nonlinear models to be tested in the context of regression. And we're going to cover the generalized linear model in more detail in lecture 23 next week when we talk about the idea of testing all sorts of nonlinear relationships. Here I'm just presenting it first in the context of binary logistic regression. So I ran that in R, and you'll see at the top of this slide the formula now, since we're not doing a regular multiple regression like we did a few weeks ago, we have to call the formula GLM, not LM. So GLM is for generalized linear model. And I just put in my outcome variable, that's verdict, and then I put in all my predictors. So this looks exactly like the LM calls, right? But now I have to add this argument family equals binomial. What that tells it is apply that logit transformation to the left-hand side of the regression equation. Then we can get all of our output, we can estimate our regression coefficients. So this GLM formula is very powerful, and there are a number of arguments that we can put in, a number of values we can put in for that argument family. Now we're just going to do binomial, but next week when we talk about the generalized linear model in more detail, you'll see there are other types of relationships we can put in the family argument. But now if you look below, the output looks just like the output that we've seen from other runs of regression. We have regression coefficients, we have the standard error of them, then we have a z-value associated with that, and a p-value. So by looking at the output here, we can see that dangerousness is a significant predictor, rehabilitation is a significant predictor, as is general deterrence. Now we can take these estimates and convert them into odds ratios. So remember from segment 1 we talked about how we could get the regression coefficients, which are for every 1 unit increase in x, the predicted change in the logit, which was a little hard to interpret. So let's convert that score into an odds ratio. So now here are the odds ratios. Again, you see the biggest ones are for dangerousness, for general deterrence. Those are the ones that were significant. I can test the fit of the overall model by looking at the chi-square associated with the model versus the null model. So the one for our model is 114. The one for the null model is 138. I can use a chi-square test to look to see if that's a significant difference. And with 6 degrees of freedom, that is a significant difference. So overall, the model is doing better than the null model, which says there's no relationship at all between the predictors and the outcome. I could do a series of walled tests that do the same thing, except now they just take the overall model and compare it to a model minus each individual predictor. So the first walled test here does that for dangerousness, and we get a significant chi-square. If we do it for rehabilitation, we get a significant chi-square, and so on. We do one for each predictor. And then those follow on the next slide. Finally, we can test again the fit of the overall model by saying, well, how well do I classify all of the cases? What percentage of cases would this model classify correctly? And it shows you the overall frequencies here and percentages, and here's the overall percentage. the model's getting 71% of the cases right. So it's doing much better than 50%. And as we saw from the chi-square tests, we're getting a statistically significant model, and we're getting individual predictors that are significant. So we're able to predict with some reliability who's going to vote for the death penalty and who will not. So again, the way to evaluate the individual predictors is through the odds ratios and the Wald tests. The way to evaluate the overall model is through the model chi-square and through classification success. And finally, if I wanted to extend this to examples with more than 2 categories on the outcome variable, then I could do what's called multinomial logistic regression. And the way that works is it's sort of like dummy coding back when we had more than 2 categories on a categorical variable. We just set one group as a referent, and then we would have multiple logistic regression equations formed to compare each level of my category to the referent. That's sort of beyond the scope of an introductory statistics course and would make this lecture a little bit too long, but hopefully you could see how you could extend that out if you had a categorical outcome variable that had more than 2 levels. You would just do multinomial logistic regression. Conceptually, all the other pieces would be the same.